Hey guys, how are you doing today? My name is Thomas Nield. Today I want to talk to you about using Kotlin for data science. So before we get started, let me just do a quick show of hands. How many of you have worked in a data science or data engineering capacity before? Okay, that's actually a little bit more than I expected. That's awesome. So what I'll do is, in this class, I will focus on, just very briefly, what is data science. The definition has changed and gotten more broad in the past 7 years, and I'll just go ahead and clarify for everybody in the room, in the highest level definition, what data science is. And then after that, we are going to talk about what challenges currently exist in data science, and that will segue nicely into what Kotlin can do to help alleviate those pain points. And then I have a few example applications I threw together, and then I will talk about how all of us in this room can get involved. So even if you're an Android developer, there is a lot of opportunity to help on the data science front in large and small ways, and I will show a few means that can be done. So just a quick note about yours truly. My name is Thomas Nield. I'm a business consultant at Southwest Airlines in the department that comes up with schedules and optimizes them. And I'm also the author of 2 books, Getting Started with SQL by O'Reilly, as well as Learning RxJava by Packt Publishing. I'm a trainer and content developer at O'Reilly Media as well, and I'm an open source maintainer and collaborator for a number of projects, including RxKotlin, TornadoFX, RxJavaFX, Kotlin-Statistics, which I have a few examples for, and RxKotlin-FX and RxPy. So we'll start with what is data science. Covering first, what is not data science? So I am developer. He actually posted a really funny tweet earlier this year. He said, "You say we added AI to our product. I hear we added a bunch more if statements to our code base." And I thought this was really funny, so I actually replied back, "The AI is smart enough to recognize several variants of a text keyword, but in reality, I actually used a regular expression." So people are very eager to describe what they do as data science or artificial intelligence and machine learning. And clever coding, while it is helpful, that's not necessarily what data science is. It's more about the objective and the means you are trying to achieve. Oops. And so data science at the highest level, it attempts to turn data into insight. That is it. That is the highest level definition you come up with, and I think that is the one thing that will always be static about it. And then the insight can be used to aid business decisions or create data-driven products. That latter part, create data-driven products, is critical, and that is going to be a driving point in this presentation. And a strong data science professional has some mix of programming, hacking, math statistics, and business domain knowledge. So those 3 domains are what defines a data scientist or a data science professional. And if you look at this Venn diagram, this is anecdotally what I've seen to be the most accurate. So between math statistics, programming, hacking, as well as domain knowledge, there are 3 overlaps that go into modeling and ML, which is machine learning, analysis and research, as well as data engineering. Now, finding somebody who's proficient in all of these things is very rare, and it's becoming more rare because big data is only complicating things even more. And so therefore, that's why the unicorn is in the center. So most data science teams, they have a balance of all 3 of these skill sets as well as those intersects. And of course, there is a lot of data science tools out there, and depending on what you're proficient in or what you gravitate towards, that will often drive which of these tools you use. Now, don't read too much into the placement of those tools, but roughly that is where tools are used within that Venn diagram. Okay, so I'm just going to very quickly just go through a subjective categorization of the different data science professionals out there. In reality, these individuals will probably be a combination of 2 or 3 of these profiles, but here's just a subjective categorization. So the statistician is the classic data scientist. This is the person who summarizes data using classic statistics models and uses probability metrics. And the mathematician, this is the person who likes using the words vectors and matrices a lot. And they probably have the most esoteric knowledge out of the bunch. And the data engineer is an architect of big data solutions, there's that buzzword, and essentially that role is making data usable to the rest of the team, especially people who do machine learning as well as statistics, and transforming and loading it in a format that can be consumed by them, and making them available through reusable APIs, ideally. So the machine learning scientist is a more advanced mathematician who leverages machine learning, neural networks, and other forms of AI modeling. The programmer, this is the person who builds all the tools that everybody has on their desktops in the office. This is a trained software developer who likely knows Scala, Java, or Python, and creates code from scratch tailored to very specific business problems. Last but not least, there's the bard, and this is the person who crafts communications about data fightings with leaders and stakeholders, often telling stories with memos, charts, PowerPoints, Tableau, infographics, spreadsheets, and other visual tools. Okay, so a term that is thrown around a lot in any data science team is a model. So what is a model? So it is essentially a concoction of math and code. It's a code representation of a problem, often mathematical in nature, that offers a solution in some form. So some examples of models that data scientists may come up with solving very specific business problems. A linear programming system that finds optimal values for business decision variables and to operate on those variables. And the machine learning model that clusters customers based on their attributes. Marketing functions love doing this. They love categorizing their customers and clustering them into different groups based on their attributes. And then artificial intelligence that parses, interprets, and links legal documents, essentially automating a lot of paralegal work. And there's a couple of startups doing this. And also a neural network that identifies or categorizes images or natural language, which is probably the most cited example that is probably the most productionized as well. Okay, next let's talk about the challenges that exist in data science, and this theme is growing more and more every year, I have noticed. A model is not a product. That is the driving point I want to bring home. So a current struggle in data science is putting models into production. So a model is often a hacky Python or R script that simply does not plug into an existing enterprise ecosystem that is often built using Java or .NET. There are exceptions. Some people do build on Python and build their entire architecture around that, but there's that article that went viral recently talking about startups grow up to become Java shops. I'm not going to reiterate those points. And models often use dynamically typed languages with tabular data structures and procedural code, which is difficult to modularize, test, evolve, and refactor. So this means that rewriting models as they're keeping improved, it's not uncommon that they get rewritten from scratch multiple times. And this is a really big point. If a model starts to break down and starts to produce errors, it can bring into question the data scientist's credibility. So this is actually a pretty common story, anecdotally, I encounter, where a concept a data scientist comes up with is great, it sounds perfect, there is no reason why that shouldn't work, but the execution does not go so well. And this is my opinion, it's often because of the technology they use as well as the practices that are put into it, and that's something we will start discussing. So what actually happens is models often need to be rewritten from scratch as software once it's usable, and that is what the product should be. And software engineers often have to port it from scratch, from Python or R to Java, and they have to modularize it and open it up so its inner workings can be presented in front-end software. Because essentially it's just one big black box, and that black box needs to be transparent, when it's put into an application on how it actually is working and create an audit trail. And the engineer may even have to introduce production data to the model, as the model may have only been tested with dummy data. This is actually fairly common, where a model was built with a dummy set of data or a static data dump, but when you plug it into production, it actually starts to blow up, and there are things the model did not account for because using the production data reveals very different dynamics. So the production code, I think I might have mentioned this, needs to be architected to be scaled, refactored, reused, and be tested thoroughly. Just a couple of real-world examples of people expressing these sentiments. So Robert Chang, who was a data scientist at Twitter, he's now at Airbnb, he said, "There was only one problem. All of my work was done on my local machine in R. People appreciate my efforts, but they don't know how to consume my model because it was not, quote unquote, productionized. And the infrastructure cannot talk to my local model. hard lesson learned. So this is literally a case, and there's many of these, where a model never left a data scientist's laptop and it never saw production. And then Jeff Magnuson, he is a director of data at Stitch Fix. He said, data scientists are often frustrated that engineers are slow to put their ideas in production and that work cycles, roadmaps, and motivations are not aligned. By the time version 1 of their ideas are put into production, they already have versions 2 and 3 queued up. Their frustration is completely justified. So essentially what's also very common is when you actually start successfully rolling out models as software, you have to maintain 2 versions of it, the data scientist version in Python or R, and then you actually have the production version that's written in Java. And those two, as they start to grow in complexity, can become more and more disconnected, or that risk starts to increase. And then Josh Wills at Slack, he is the director of data engineering. He summarized this pretty aptly. He presented this diagram and just called it the infinite loop of sadness. And as you can see here, the data science function is siloed from the rest of the organization, fails to kind of get integrated into the DevOps cycles as well as the software engineering functions, and again, just expressing the exact same sentiments. And this is actually a very good article called Data Science Gophers. It was published by O'Reilly. It was written by Daniel Whitenack. And he proposes using Go as a data science language, but largely for the same reasons that I am expressing right now. So Kotlin is a valid option too, which I'm going to get into next. But that's a very good article, basically expressing the problems with productionizing data science. So why Kotlin for data science? And so what is the solution to all of these problems? Kotlin, of course. That's why we're all here. And data scientists who code often need the following. They need rapid turnaround, very quick iterative development, they don't have very much tolerance for boilerplate code. They need something that's easy to learn, and they need a very flexible code language. They also need mathematical and machine learning libraries. Now, experienced software engineers often want the following. They want static typing and object-oriented programming. That's increasingly becoming apparent, a good way to make things maintainable. A production-grade architecture and support, and then also refactorability, reusability, concurrency, and scaling. So Kotlin actually encompasses a lot of these qualities on both sides and can actually meet the needs of both parties. And it can close the gap between data science, data engineering, and software engineering. So what I'm proposing is one language, one code base, one platform. So data engineer, data scientist, software engineering / DevOps. Everybody's working on a Kotlin code base. Meaning software engineering can even keep Java, and they can work in Java, but you can use Kotlin to interop. And the data engineer and the data scientist can model things in Kotlin, and then the software engineering side can refactor it, not have to rewrite it, and actually make it usable for production, and create that whole collaborative workflow between all parties. And on the technology front, have it break down those silos. Okay, so just a very quick comparison of Kotlin versus the incumbent data science languages out there. I didn't include a comparison to R because that's really not fair to compare R to Kotlin or Python even, primarily because R is very focused on mathematical modeling and not really much else. It's not really a general purpose programming language like Python is, and that's one of the reasons why Python has been getting more traction. So Python is a powerful, flexible platform with a simple syntax and a rich ecosystem of libraries. It definitely adds value to an organization. However, dynamic typing makes Python flexible for ad hoc analysis. Dynamic typing really does seem great when you can just import a text file and it creates objects off that text file for you. But this can be challenging to use in production. So dynamic types allow improvised data structures to be defined at runtime. And dynamic typing can quickly create difficulties in the maintainability and testability of code bases as well as the debugging. And this problem only grows worse as the code base grows. It requires more upkeep. So Kotlin, like Scala, embraces immutability and static typing. Its types are always constant once it compiles. And data structures are explicitly defined and enforced in compile time, not runtime. And while static typing is traditionally verbose, which Java's gotten a reputation for, Kotlin manages to make it concise in a Pythonic manner. So the elephant in the room is that Kotlin may not have as many mainstream data science libraries like Python does, but it does have comparable ones in the Java ecosystem. So Apache Spark, of course, that works with Kotlin perfectly because it has a Java interface. Kotlin-Statistics, there's even some Kotlin-focused data science libraries in development. So Kotlin-Statistics, which I have developed this year and I'm going to show a few examples from. There's also Krangle, which is a data frames library, as well as Coma and computation. And OJAlgo, this is actually a library I've been having a lot of fun with. There's a lot of Java-based data science libraries out there, and Kotlin can plug right into those, and you can actually, very easy open source opportunity, just put some Kotlin extensions around them and actually make them much more usable. And then you can actually build more features on top of it because Kotlin offers that ability. And OJAlgo, that's actually a library I've been having a lot of fun with. It's a linear programming library, and I have an example for that in a moment. Okay, so Scala. So Scala has seen success in adoption on the data science domain, arguably due to Apache Spark and other big data solutions. So it was going to be the big data language, and it still kind of is. However, and I'm going to try not to be anecdotal about this, I'm just going to try to stick to what I know. Scala might have some challenges going forward. Apache Spark is being interfaced in other languages like Python and R to make it accessible. And also, computation engines, so when heavy number crunching needs to be done, all that heavy matrix work, those are increasingly moving back to C and C++ and away from the JVM and letting languages such as like Scala, Kotlin, Python, R interface with those libraries. And one of the reasons why Scala might not have gotten as much traction as people thought it would is the plethora of features. Is it good or overwhelming? Going from Python to Scala is a huge leap. Python, and I'm going to get into this point next. So Python actually limits its features, and that appeals to people, where Scala has plenty of features, most of which you may not even want or need. I'm trying not to be anecdotal or try to put any bias into this, but there's a lot of features in Scala that are very experimental, and some of them actually end up being used heavily, others become a little bit more niche. So Scala not taking significant share from Python may present an opportunity for Kotlin. So Kotlin might be able to finish what Scala started, establishing an engineering-grade coding platform for data science. And compared to Scala, Kotlin has much easier interop capability with Java. And it arguably encompasses many of the best ideas from Scala, but strives to be simpler in its features and be more accessible. If you ever heard the term Pythonic, this is what Python developers describe as code that's legible, it's concise, it's easy to read, it's easy to figure out what's going on. And I think Kotlin actually has those features too. And while computation engines are unlikely to be dominated by Kotlin implementations, now this may not be true anymore because of Kotlin native, it might actually do really well there. But Kotlin can at least be effective in interfacing with those engines. Okay, so I'll just get this slide over with. Weaknesses of Kotlin for data science. So there's not really too many drawbacks, but it would be remiss of me not to cover these just so that this is something that could be worked on or could be addressed. So Kotlin is not dynamically typed, and data structures have to be explicitly defined, which can add additional steps in working with data. So many of you in this room is like, well, wait, doesn't that have a return on investment once I do that? And I agree with that sentiment. Yeah, it does, because working with the data, when you have it explicitly mapped to domain classes, you have much more guarantees that that data structure is going to work as, in a very hard defined way. Boxing of numbers might hurt performance without ND4J and other low-level computation libraries. So JVM, it's boxing and numeric performance. This might change with Project Valhalla. It can hurt performance when you're doing heavy amounts of computation, but there are libraries like ND4J, which is Java's NumPy essentially, that can do that kind of work for you. It'll be interesting to see what happens with Kotlin native too. And libraries and toolings. This kind of goes back to the whole not dynamically typed thing. So the ad hoc analysis, casually exploring data without a clear objective, may be challenging without data frame libraries like Krangle. So if you're given a text file and you want to open it and just see what's inside, you can't create a class for it unless you actually see what's in that text file. So you can't just import it in a data frame unless you're using a data frame library like Pandas does, and Krangle's kind of similar to that. And the breadth of data science libraries, while decent, does not match Python or R. This doesn't really concern me too much because Python spent a good 4 or 5 years catching up to R in terms of libraries, and it got there. I think Kotlin in general could catch up to that too, if the community was actually to contribute towards that initiative. And this one makes me pause for a moment, although this is probably going to be a problem on Android too, documentation. So Java libraries use Java, not Kotlin, in their documentation. So if Kotlin's a first language somebody learns for the JVM, and they want to use a Java-based library, they have to look at the documentation in Java. And whether they can overcome that or not, I don't really know. I guess it depends on the person. And that's something that Android, I think, will address as well. We'll have to address as well. Okay, the strengths of Kotlin for data science and data engineering purposes. So accessibility, it's easy to learn. There's not that many features, and there's not that many features to make it overwhelming like Scala. It's not that esoteric. Kotlin does not try to be clever. It just tries to get things done. And it has that Pythonic productivity, offering minimal boilerplate and fast turnarounds. And I think the Pythonic thing, I think that's really a big reason why Python has gotten so much traction in data science, because a lot of data science professionals, they come from very diverse backgrounds, many of them not technical at all, so Python was a very easy language to pick up, is the easiest language to pick up. And I think the Pythonic qualities actually is one of the reasons it got so much traction. And I think Kotlin has a lot of those Pythonic qualities as well. And of course, interoperability with Java, it plugs into enterprise Java ecosystems, therefore helping make models much more easily transitioned into a product. And then language features. So data classes, I love data classes. I know they kind of existed in Scala before, but not having to create tuples or improvise data structures anymore, it creates a lot more productivity, and it enables you to quickly map each data record or data element into a class, and it's immediately printable. You can actually modify it using those copy and clone functions. And DSLs, and actually I remember Hadi posed this idea one time, and actually I found this really interesting. So you can create streamlined languages for domain-specific logic. So if you have non-technical people that you work with and you want them to interface with a model and to play with it, you can actually use DSLs to create a very specific language just for that model's purposes or for that business problem that's being solved, and they can interface with it that way. I mean, you could also use like a TornadoFX UI or whatever, but that might take less effort. And then static typing, so the benefits of OOP and static typing without the verbosity. Nullable types, I actually have found a surprising amount of value in this. So when you're working with data, it's very easy when you get access to data for the first time to make a lot of assumptions about it. And before you know it, you're modeling all this logic around it, and you did not realize that some nulls actually slipped into there. And so the nullable types, especially when you're mapping data to classes and all of that, and you explicitly say this is null or this is not null, it proactively stops that very common problem from ever seeping in the first place right early in the process, rather than trying to debug it much later after you've built your entire model. And so function syntax, lambdas and pipelines, these are things, in my opinion, that Python really lacks in, and I cannot live without these. Using higher order functions especially. I mean, Python does have lambdas and it does have functions, but they're not really as flexible as the way Kotlin executes it. Okay, so I have a few example applications, and thankfully I'm doing really good on time. So I'll walk through a few modeling examples that I threw together. I'll get the ambitious one done first. So let's look at linear programming, and this opens up a very huge amount. This opens up a whole domain of app development. Just by learning a little bit of math, there is a wide number of problems that could be solved and apps developed for. So you have 3 drivers who charge the following rates. Driver 1 charges $10 an hour. Driver 2 charges $12 an hour. Driver 3, $15 an hour. Okay, so from 6 o'clock to 22 o'clock, you need to schedule one driver at a time to provide complete coverage, but you want to minimize the cost. So far, this doesn't seem so bad, but here's the catch. Each driver must work 4 to 6 hours a day. Driver 2 cannot work after 11. So this is a very simple, very self-contained example that's small enough for me to speak on it in just a few minutes. But imagine if you had 1,000 drivers and you need to schedule 100 of them at a time, and you need to schedule them in different areas geographically. So linear programming is used very heavily to solve those kinds of optimization and operational planning problems. And I went through the Android App Store, and I really did not find apps to do like, university, like classroom scheduling or staff scheduling, and there is a very wide array of problems that could be solved just learning a little bit of linear programming, which is not as hard as it sounds. Okay, stay calm. So, if you know just some basic high school algebra and you're not intimidated by some Greek symbols, which really are just variables in the programming side in the end. So for example, SI on the far right, so S subscript I, this is the shift start time for each I driver. So each driver is going to get their own start time variable. There's also the end time, the hourly rate. Those are defined as variables for each driver. And then there's this binary, this, I forget what the symbol's called, this Greek symbol. But that's a binary, a 1 or a 0 between two drivers, just to make sure those drivers never have their shifts overlap. So basically using that binary will prevent the shifts from overlapping and that only one driver is working at a given time. So this minimize function at the bottom, that is what I'm trying to minimize. I'm trying to minimize the sum of the rate times basically the driving period for each driver, so the end time minus the start time of the shift. And to the right are the constraints based on that word problem that I defined. And again, this is just this is just not terribly advanced algebra. And I'm using inequalities to express, like it can't be any higher than this or it can't be any less than that. And this summation symbol right here, that is just basically saying the sum of all the shifts must equal 16, just to guarantee that I have covered the shift for the entire day, or I have the entire day covered. So by just taking those mathematical functions, which really is where most of the work is done, and I actually have built this model in OJAlgo. So I used a library called OJAlgo, which is one of the few libraries that's actually pure Java. It doesn't actually use it doesn't use C or C++, at a native level, but it actually runs really quickly. So I've been having a lot of fun with this library, and what I've done here is I kind of took OJAlgo, improvised a DSL around it to make it a little bit nicer, and I declare a list of drivers right here, driver objects, only 3 properties, the driver number, 1, 2, 3, the rate, hourly rate they charge, and if there's a certain availability I need to constrain them to, I pass the availability as an optional argument. That's a nullable type, I think. And then I just declare 2 variables, operating day and allowable shift size. And I just use a Kotlin range for that. And I'm going to go through each of the drivers and call its add to model function, and I'll show what that does shortly. And then I'm going to call minimize on the OJAlgo model so it'll go find a solution that minimizes the cost for all those drivers but does not break any of those constraints we defined. So on the model side, what I just want to highlight here is I have this driver class where most of the work is actually happening. So again, those are the 3 properties, driver number, rate, availability, which is a nullable int range where it could or could not be provided. And then this function called add to model, or actually, let me highlight this too. The shift start, shift end, those are 2 OJAlgo variables. I weight them with the hourly rates. I say the start time and end times can't be any lower than 6 o'clock, but no later than 22 o'clock. And then the add to model right here, this will go and input each function that I defined on that slide we looked at earlier. And it will add each function to the OJAlgo model. Now, this may not look immediately apparent how I took that and then turned it into this fluent builder construct right here. But basically, I just turned it into a vector where I just extracted the multipliers, and I made 0 only exist on one side, and I just did some algebra to do that. So what's really cool here, though, what I want to highlight is that rather than just dumping a pile of numbers or dumping a bunch of matrices, I am actually solving this problem in a very object-oriented way, and that's very refactorable. And I can actually add more constraints. So if I have new rules I need to add, I can go ahead and just add another function call here to pass another mathematical function. And then I can remove them as well. So this makes a lot simpler implementation. I can change this, modify it, not have to rewrite it several times, just because I've kind of solved this problem using a grid of numbers, which is pretty common, but solving it in an object-oriented way, it actually comes out really clean. And this is a really, really good standard, in my opinion, to strive for. So I'm going to run this. And I'm going to print the driver as well as the value of the variables after it's been optimized. So the optimized at $936 is the total cost, saying that is the lowest cost I can achieve. And to achieve that cost, I schedule driver 1 from 16 o'clock to 22 o'clock, driver 2 from 6 to 10 o'clock, and then driver 3 from 10 to 16 o'clock. So think about it. You could actually create so many apps using this kind of solution, and that's just linear programming alone, and that opens up a very large domain. So you can solve things like schedule generation, classrooms, transportation, staff, operations and resource planning, construction, factory planning, as well as blending problems for financial portfolios, as well as optimizing mixes of food and drink ingredients. So saying, I need the quality of this food item to be this, but I want to minimize the cost using these 3 different sources for that ingredient. And see, that's just one area of data science that is one way you can kind of get involved with it and actually use it to turn into products. And Kotlin, and what I want to highlight too is Kotlin makes it easier than ever to make a model a finished product. So that model I created with the linear optimization of those scheduled drivers, I could very easily refactor that really quickly, wrap that all up in a class rather than defining all these constants, and then put a user interface around it or put it on a backend. And if I have to scale it for big data, that's a whole different story, but still, I am using something that actually could be put into production, whether it's locally running on the Android app or it's running on a server. And Kotlin is capable of solving a wide array of problems for many data science topics. Okay, before I move on to that slide, I'll show just a few more examples very briefly. Okay, so here is just an example where I just use Kotlin standard library, absolutely nothing else. So I created this very simplified social network right here that I modeled. I have social users, which has an ID, a first name, last name. And then I link friendships between these people just using numeric pairs, just pairing the IDs saying these people are friends. And so I encapsulate that into a social user class. And then what I can do is, in a very object-oriented way, I can create all these functions inside that user to solve different tasks, such as what are that social user's friends, and I'm using sequences to achieve that. And what are the mutual friends between another user, and I have a function to support that. And then this task sounds like it may not be that complicated, but it kind of is. Getting recommended friendships between two people, getting recommended friendships for a given person by essentially finding who they're not friends with and who they have mutual friends with that person, and then using that to drive a recommended friend algorithm. And again, this was all done in this one class. I mean, very little boilerplate. The Kotlin sequences do a wonderful job at that. So if I go and extract the user whose first name is John, and I go and loop through his recommended friends, there are the 4 people it recommends you be friends with. So that was just using the Kotlin standard library. Okay, so Kotlin-Statistics. So I started working on this library around summer of this year, and I just released it to 1.0 before this conference. Essentially what I wanted to do with Kotlin-Statistics, it was an experiment to see if I could actually analyze a collection or sequence of objects without resorting to data frames and other tabular structures. And it actually ended up working really well. So for instance, I have this list of products. Did I paste something? Hold on. Yeah, I did. Okay, so I have this list of products right here. And it's just 5 different properties on that product, including a defect rate. And I can use higher order functions to very quickly group up the items and create some aggregate total on them. So for instance, this is a simple example. If I just want to get the count by products, I just call the count by function, and I pass what I want to count it by. So if I want to get the counts by category, I can use a higher order function in Kotlin-Statistics to do that. And if I want to get the average defect by category, I can call the average by extension function, and I pass two higher order functions what I want to key on, and that can actually be a data class if I want to key on multiple fields, and a double selector to say what am I averaging, which field am I averaging. So let me go ahead and run this. So for that list of products right here, there is the counts by category as well as the average defect rate by category. So what was really satisfying when I was working on this project is like, okay, so actually I can do some meaningful statistical analysis in a very object-oriented way mixed with functional higher order function programming. So another thing that Kotlin-Statistics does, and I based a lot of Kotlin-Statistics uses Apache Commons math, but I did add a few additional functionalities to it, which I'll show shortly. That group by operation, Apache Commons math didn't do that because idiomatically it wasn't really, there was not an easy way to do that. And so Kotlin made it easy, so I implemented that feature on top of it. So here's another example. So if you guys have not used TornadoFX, it is a great desktop framework based on JavaFX that Edwin Sisa made. And it's also really great to quickly throw a desktop UI together and also do a little bit of charting. So I'm going to do some, I have this list of patients right here with those properties, most notably that white blood cell count I want to hone in on. So if I want to cluster these patients by their age and white blood cell count, I'm going to call that list of patients I've instantiated, and I'm going to call the multi-k-means cluster. And what this is just one method, you can look at the README for Kotlin-Statistics, that will just cluster the points using a certain methodology to say, okay, these points are kind of in proximity to each other. And I basically pass arguments and some higher order functions mapping the x-axis to a certain property and the y-axis to a certain property, so age to white blood cell count. And then I'm going to call the scatter chart function around that entire call and add each of those groups to a series, which will plot each group in a separate color. I'm also going to display it in a table next to it just for good measure. So go ahead and run that. Okay, so very low code, and I just threw together a dashboard. Really nice desktop UI. If I wanted to add some toolbars, buttons, and everything, and other controls, I could actually turn this into a software product pretty quickly. But as you can see here, it took those patients and it clustered them based on whatever clustering parameters I passed to it. So it's very nice because it's very flexible, but it's very idiomatic, and I can just turn things around very quickly, which data science often requires. And then last example, binning. So Kotlin-Statistics actually has binning operations. So let's say I have these sale objects, which is just an account ID and a date and amount, and I want to bin them by quarter. So what I can do is I can just call the bin by comparable function in Kotlin-Statistics, select what value I am binning on, how large each bin is, so it's going to be 3 months, that's going to be the size of the bin, and the incrementer just to give it a notion of, since it's comparable, not a numeric type, how it's supposed to increment the local date. So I'm just going to add 1 month to it. And then I'm just going to print each of the bins, and I'm going to go look up the bin for the month of February. There we go. So I have taken those objects and I have binned them up by quarter based on those buckets of 3. Okay, so let me go ahead and go through the closing slides. Looks like I have a few minutes left. Okay, so help bring Kotlin to data science. There are ways you can get involved. You do not have to go and get a PhD in data science at all. There's many different ways to enter data science, even casually. And what I recommend is just learn the areas that interest you first. So linear programming, graphing visualizations, machine learning, even doing data wrangling, so just actually making data useful, making it in a format that actually presents something that's a little bit easier to consume. And also create some data-driven projects with Kotlin and share them. So write some blog articles when you do this, put some data-driven features in your apps, And open source libraries, like I said earlier, if you take existing Java libraries and put some Kotlin extensions around it, you can make it much more usable, and that may actually make that library appealing to use. And I also want to emphasize, never stop researching, learning, and advocating. So although it's incredibly difficult to achieve, never stop striving for that unicorn status. And keep struggling to learn math, statistics, machine learning, and find ways to make what you learn useful. And if you're learning something and say, I don't really know how to use this, well, move on to something else. At least you're aware it's there now. And introduce data-driven features into your apps and share how you did it. And if you work on a data science team or you're working with a data science team and there's a need to put models into production, propose Kotlin as a possible solution. So anyway, guys, thank you very much for coming to this session. It has been awesome speaking with you. Thank you, JetBrains, for putting this event together. If you guys have any questions, feel free to ask me back there out in the lobby. You'll see me wandering around. But thank you. You guys have been great.